Hi, in this video, we will discuss about the problems of ordinary differential equation from CSIR NET 2013 December exam. Okay, and in last video, we have solved all the problems from ordinary differential equations which are asked in 2013 June. So let's start today's video. Here is the first question, question number 41. Let gxy be the Green's function of the boundary value problem. This is the boundary value problem. And here two conditions are given. Then the function g defined by gx is equals to this, capital G x, comma half. Okay. And x is from closed interval 0, 1. Then we have four options. Option A, this Green's function, this function g that will be continuous. That will be, this is discontinuous at x is equals to half. This is differentiable and does not have left derivative at x is equals to half. So before solving this problem or before discussing the options of this problem, let me show you some properties of Green's function. Here we have some properties of Green's function. First one, Green's function is symmetric. Number two, Green's function satisfies the given equation. That means given differential equation. Okay. Number three is gxt. That means the Green's function that will be continuous and has derivative up to n-2 order. Right? If gxt, if the differential equation is of nth order, then the gxt that will be continuous and it will have derivative up to n-2 order. Right? Number four is n-1th derivative has a discontinuity of first kind at x is equals to t. That means del n-1 g del x n-1 at x is equals to t plus minus del n-1 g del x n-1 x is equals to t minus this is equals to minus 1 by p0t. And what is p0t? This is the coefficient of d2y dx2. Or you may call the double derivative, coefficient of the double derivative of the given differential equations, right? And number five property is gxt satisfies the boundary conditions. So if you take a look on the option A is saying that this is continuous, right? And here given that gxt, this is continuous, okay? That means option A, this is satisfying the property of Green's function. So option A, that will be the correct options. And all other options discontinuous, this is incorrect. Differentiable, not differentiable everywhere. This is n-1th derivative has a discontinuity of first kind and here given has derivative up to n-2 order, right? So option C, that will be incorrect and option D is also incorrect, right? Next question. Question number 42. Let W be the Wronskian of two linearly independent solutions of this ODE 2y double dash plus y dash plus t square y equals to 0 and t is from real number. Then for all t, there exists a constant c belongs to R such that WT is Wronskian equals to what? So here the given differential equation is this 2y double dash plus y dash plus t square y is equals to 0. And we can compare this equation with our general form of second order differential equations. And we know that Wronskian W, this is equals to c e to the power minus integration a1 by a0. A1 that means coefficient of y dash and a0 that means coefficient of y double dash dt. Okay, and we are getting W equals to c e to the power minus t by 2. And if you check the options in option B, it is given c e to the power minus t by 2. Okay, so option B, that will be the correct option. Next problem. Question number 91. This question is from part C, that means 4.75 marks, and one or more options can be true. So what is the question? Let y be the let y be a non-trivial solutions of the boundary value problem. This is the boundary value problem, and these are the boundary conditions. Now we have four options. B, that will be greater than 0. Y is monotone in open interval A0. Y dash A equals to 0. Y has infinitely many zeros in closed interval AB. Okay. Let me tell you, if we compare this equation y double dash plus xy equals to 0 with this form y double dash plus pxy equals to 0, and we have two results. If this px is positive, then every non-zero solution will be oscillatory type, okay, and it will have infinitely many zeros. And if this px is negative, then it will be the solution, non-zero solution will be either strictly increasing or strictly decreasing, and it will have at most 1 0, right? Now check that here given ya equals to yb. Here given that ya equals to yb equals to 0. That means the solution has more than 1 0. Here a and b, these two are zeros of y. Okay, so it is clear that x, this x is not less than 0, because here given if px this is less than 0, then this will have at most 1 0. So x, this is not less than 0, so x will be greater than 0. Okay, so x is greater than 0 and x belongs to closed interval AB. X belongs to closed interval AB. We cannot say about this A, but since x is positive and x is in between of A and B, then it is clear that B will be also positive, right? So in option A, it is given B is greater than 0. So option A, that will be correct. Okay. Now, here given when px is greater than 0, the solution it will have it will be oscillatory type and it will have infinitely many zeros. Now this x is positive in closed interval AB. Okay, but we don't know about A. A may be negative, may be positive. Okay, so in this interval A0, okay, in this interval x may be negative. In this interval x may be negative, and when x will be negative, in that case the solution will be monotone. Okay, here when px is less than 0, every non-zero solution is either strictly increasing or strictly decreasing. So when the interval is A0, in that case the solution may be monotone, right? So in option B, it is given y is monotone in A0 if A less than 0 less than B. This condition is necessary. If A less than 0 is less than B. For the presence of these conditions, we are saying that in this interval x will be negative, and for that y the solution will be monotone, right? So option B, that will be again correct. Option C is saying that y dash A, this is equals to 0. Let me show you here. Here, any non-trivial solution cannot have repeated zeros. And we already have that ya, this is equals to 0, this will be y. Let me check it. Yes, that will be y. We have ya, this is equals to 0, and here given y dash a, this is equals to 0. That means that 0a, this is a repeated 0, and here given that any non-trivial solutions cannot have repeated 0. That means y dash a, this cannot be 0. Okay, so option C, that will be incorrect. Option C will be incorrect. Option D is saying that y has infinitely many zeros in closed interval AB. No, this is not correct. Why? Because for any non-trivial solution, any non-trivial solutions of a homogeneous linear differential equations, our given differential equation is homogeneous linear differential equations, and it is defined on a bounded domain. Our domain is closed interval AB. This is bounded. So any non-trivial solutions of a homogeneous linear differential equation defined on a bounded domain that has finite number of zeros. Okay, and option D is saying that y has infinitely many zeros. So option D, that will be incorrect, right? Okay, next problem. Question number 92. Let y maps R to R satisfy the initial value problem. Y dash t equals to 1 minus y square t. T belongs to R. And here the initial condition is y0 is equals to 0. Then we have 4 options. So here the given equation y dash t, this is equals to 1 minus y square t. So we can write this differential equation in this form. Okay, now if we integrate this is the integration. Now if we put y is equals to sine theta, then dy, that will be cos theta d theta, and simplifying this calculation, finally we are getting this form. Okay, now our condition is y0, this is equals to 0. So if we put x equals to 0 in this here, so y will be 0, and finally we are getting t equals to 0. T equals to 0. So at the point t equals to 0, y is equals to 0. Okay, so this will be 1 and this will be 0. So c, that is equals to 1. So finally what we are getting? We are getting 1 plus y by root over 1 minus y square equals to e to the power t. And if we simplify this, we are multiplying numerator and denominator by root over 1 minus y square. So we are getting 1 plus y whole, we are squaring both sides. Then we are getting this form, and 1 minus y square, this is equals to 1 plus y into 1 minus y, and simplifying this we are getting this form. Okay, so y into 1 plus y, this is equals to e to the power 2t minus y e to the power 2t, and simplifying y into 1 plus e to the power 2t, this is equals to this, and yt equals to e to the power 2t minus 1 by e to the power 2t plus 1. Our option 1 is saying that, here is the option A. Option A is saying that yt1, this is equals to 1 for some t1 belongs to R. Okay, so let's put t is equals to t1. Yt1 equals to 1. So from this form yt, from this form, if we put t equals to t1, we are getting this figure, e to the power 2t1 minus 1 by e to the power 2t1 plus 1, this is equals to 1. And simplifying this, we are getting minus 1, this is equals to 1. And this is not possible. So option A, this is incorrect. Okay, let's check option B. Option B is saying that yt is greater than minus 1. Now we have to check this statement is correct or not. So if possible, let us consider that yt, that is less than equals to minus 1. The opposite of greater than minus 1, this is less than equals to minus 1. And taking this consideration, let's check. Yt is less than equals to minus 1. That means e to the power 2t minus 1 by e to the power 2t plus 1, this will be less than equals to minus 1. And finally, we are getting this form, that 2 e to the power 2t, this is less than equals to 0. And we know that exponential function is always positive. So this is not possible. So yt that will be always greater than -1. So option B is correct, right? Now option C. Option C is saying that y is strictly increasing in R. When we have to find out strictly increasing or decreasing property, we have to derive the function. So yt, this is equals to this, and differentiating one time. So y dash t, from y dash t, we are getting this form, 4e to the power 2t by e to the power 2t plus 1 whole square. Exponential function, this is positive, and this is a square form. So obviously this will be positive. So whole y dash t, this is greater than 0. And since this is greater than 0, so this will be strictly increasing for all t belongs to R. Okay, so option C is saying about the strictly increasing property. Here you can check it, y is strictly increasing. So option C is correct. And y is increasing in open interval 0, 1, decreasing in 1 infinity, this is wrong. So option B and C, that will be the correct options, right? Next problem. Question number 102. This problem is also from part C, that means 4.75 marks. Okay, here given a coefficient matrix A is equals to this matrix and y is equals to this. These are the solutions of this differential equation. dy dt equals to ay t greater than 0. And here the initial condition is given y0 equals to 1, 1, 1. So from here, what we can say that y10, this is equals to 1, y20, this is equals to 1, and y30, this is equals to 1, right? And from this given differential equation, if we consider that A, this is a scalar, okay. So from here, what we are getting? We are getting that suppose y is equals to our first solution y1. Okay, so dy1 by dt, this is equals to ay1. So from here, solving this, what we are getting, y1t, this is equals to e to the power t a into some constant k. Now, if we use the initial condition that y10, this is equals to 1, what we are getting? If we put y10 equals to 1, then this will be 1, this is equals to e to the power 0, that will be 1, and k, this is equals to 1. So it becomes k is equals to 1. And you may call it that, and again, this is y0 is equals to 1. Okay, so the option 1, y1t, this is equals to e to the power t a y0. This option is correct. From here, we can save. Now check all other options. A given coefficient matrix is A. This is our A given matrix. And dy dt, this is equals to ay, and y0 equals to this. This is the initial condition. So from here, what we are getting, first equation is dy1 dt, this is equals to y2. From here, dy1 dt, this is equals to y2. Okay, and here the condition is y10, this is equals to 1. Second, dy2 dt, this is equals to y3 here, and the condition is y20 equals to 1. And dy3 dt, this is equals to, there is no non-zero term in third row, that's why this is equals to 0, and the condition is y30, this is equals to 1. And these three are equation number 1, equation number 2, and equation number 3. Now we have to solve these three equations. So first we will solve this, the last equation, equation number 3. So dy3 dt, this is equals to 0. So from here we are getting y3 equals to c3, the arbitrary constant c3, and y30, this is equals to what? 1. Okay, so c3, this is equals to 1. So we are getting y3t, this is equals to 1. Now the second equation is dy2 dt, this is equals to y3, and this is the conditions. Now we will put the value of y3 from here. So we are getting dy to dt, this is equals to 1. And solving this, we are getting this from t plus c2. And y2 equals to y2 0 equals to 1. This gives c2 equals to 1. So finally, we are getting y2t, this is equals to 1 plus t. And by similar method, we will get y1t, this is equals to 1 plus t square by 2. Now check the options. In option A, you can see y1t equals to 1 plus t square by 2, y2 t equals to 1 plus t, and y3t equals to 1. So option A, this is correct. And these two options are incorrect. So option A and option D, that will be the correct options. Okay. So I have solved all the problems which are asked in 2013 December exam in ordinary differential equation section. So I think this video will be very beneficial for you. If it is helpful, then please share it with your friends and stay with us. Thank you.